everybody. We're getting ready to do lesson 7.5 part 2 today, classwork of pre-calculus math. And today's classwork lesson has got 16 points here of notebook taking. So have your notebooks out, have your notebook guides out, students. And then we got 40 points here on our classwork sheet. Have your classwork sheets out. Students, if you're in my classroom, put your name here, date here, and your period there. Students, teachers, let's go into the bell work for today. Today's bell work is sketch the graph of these functions here. Sketch the graph of those functions, and then identify any asymptotes that are involved with these functions here on the graph. And teachers, give your students about 5-6 minutes to do that. Pause your video and see you in 6 minutes. Okay, welcome back for the solutions for today's bell work. 103 here, f of x equals x squared minus 2x minus 3 over x minus 4. So we have here a situation here, our dividend here for this quotient will be x plus 2 plus 5 over x minus 4. So in this case here, our vertical asymptote will be x equals 4. That'll be a 0 here in the denominator. That'll be a vertical asymptote, be over here. And then we have a slant asymptote here of x plus 2. So we have a slant asymptote of x plus 2 for this function here. So the graph of that will look like this. You have something goes like that, something goes like that. Then here's your vertical asymptote at x plus 4. So there's your asymptotes, and then here's your graph of that. And then for down here, we have a vertical asymptote at -1. This will be a 0 in your denominator. So here's a vertical asymptote over here. And then we have a slant asymptote here of x minus 1. So it'd be something like down here, like this down here. So here is your slant asymptote. Here is your vertical asymptote here at x equals -1. And then you have like a hyperbolic kind of function graph like that. So there's your solutions. Let's go into today's lesson. Page 1 goes in your notebook. Students, have your notebooks out, notebook guides. The properties of matrix addition and scalar multiplication are similar to those of addition and multiplication of real numbers. One important property of addition of real numbers is that the number 0 is the additive identity. That is, c plus 0 equals c for any real number c. For matrices, a similar property holds. That is, if A is an m times n matrix and 0 is the m times n 0 matrix consisting entirely of zeros, then A plus 0 will equal A. In other words, 0 is the additive identity for the set of all m times n matrices. For example, the following matrices are the additive identities for the sets of all 2x3 and 2x2 matrices. So this goes in your notebook, students. So here we have a 0 matrix here, and then here's a 0 matrix here. This is a 2x3, and then this is a 2x2 matrix there. So here is a 0 matrix, 2x3 0 matrix. This is a 2x2 0 matrix. Properties of matrix addition and scalar multiplication. Let A, B, and C be m times n matrices, and let C and D be scalars. So number 1, A plus B equals B plus A. That's the commutative property of matrix addition. And number 2 here, A plus the quantity B plus C equals a quantity A plus B plus C. So we have the associative property here of matrix addition. And then we have number 3 here, CD times A equals C times D times A, the associative property of scalar multiplication. And then number 4 here, 1 times A equals A is scalar identity. 5, A plus 0 equals A. Then we have the additive identity. And then number 6 here, C times quantity A plus B equals C times A plus C times B, distributive property here. And then number 7, be quantity C plus D multiplied by A equals CA plus DA is the distributive property. So let's try an example here that contains these properties, okay? So using distributive property here, we have 3 times the quantity of this matrix plus this matrix equals what? So, okay, so we can put this in brackets. We can put this into more of a brackets now. 3 times negative 2 is 0, then 4, 1, plus 3 times. We're going to use our distributive property here of multiplication, then 4 and negative 2, 3, and 7. And then that will give us 6, negative 6, 0, 12, 3, plus 12, negative 6, 9, 21. And then when we combine these two matrices, we have 6, negative 6, 21, 24. So let's try one now. Evaluate the expression. So we have 4 times quantity of these two matrices here. Down here in your independent practice, students, you have 1/2 times quantity of these two row matrices added together. Let's focus now on our guided practice up here. When we do this, we have 4 times this minus 4 times that. So we have 4 times, first, remember our order of operations, negative 4 minus, all these starts, we have a sign change over here in this bracket. 4 minus negative 4 minus 2 will give us negative 6, then negative 1, and then 1 and positive 3 will be 3, and then etc. here. So we have 4 times this now. We do our subtraction first, and then we multiply these out by 4, and then we end up with this 2 by 3 matrix here. And then down here, again, you do what's inside your parentheses first. You do your PEMDAS here. 5 and 14 is 19, negative 2 and 6 is 4, 4 and negative 18 is negative 14, and 0 and 9 will be 9. And then we multiply through by 1/2, and we end up with this row matrix here for that one. Okay, moving on now. In example 5, you could add the two matrices first and then multiply the resulting matrix by 3. The result would be the same. The algebra of real numbers and the algebra of matrices have many similarities. For example, compare the following solutions. Now, real numbers solve for x, and then m times n matrices solve for x. So we have x plus a equals b, and then x plus a equals b. So comparing those two different kinds of situations here, x plus a plus a negative a equals b plus a negative a, and then x plus a plus a negative a equals b plus a negative a. So we have x plus 0 equals b minus a, and then this will be x equals b minus a, and then over here we have x plus 0 equals b minus a, and then x will equal b minus a. So you'll have this, the algebra will produce the same kind of result here. The algebra of real numbers and the algebra of matrices also have important differences, which will be discussed later. So let's go into another example here. Example 6, solving a matrix equation. Solve for x in the equation 3x plus a equals b. So where a equals this matrix here, and then b equals this matrix here. Begin by solving the equation for x to obtain 3x equals b minus a. Up here, 3x equals b minus a. And then this gives us x equals to 1/3 of b minus a. So this is what x will be when we solve for x. Now using the matrices a and b, you have x equals 1/3 of b. This is our b here. B is here. Then our a is over here. So now we have that. Now once we have that, subtract matrix A from matrix B. So then we end up with this here, -4, 6, 2, and -2 when you subtract matrix A from matrix B. So now when we multiply through by 1/3, we have -4 over 3, 2, 2/3, and -2/3. Multiply the resulting matrix by 1/3 now. So let's go into our next example, which is this here. Solve for x when a equals this and b equals that. And then 31 here, this is 2x plus 3a equals 3a equals b. So here's our a and here's our b. So how do we solve for x in this situation here? So when we do solve for x here, we get x equals -3 over 2a plus 1 over 2b. And then when we, you go ahead and solve the rest, students. Page 11, matrix multiplication now. Another basic matrix operation is matrix multiplication. At first glance, the following definition may seem unusual. You'll see later, however, that this definition of the product of two matrices has many practical applications. So the definition of matrix multiplication, if A equals bracket Aij is an m times n matrix and B equals bracket Bij is an n times p matrix, then the product of AB is an m times p matrix given that AB equals bracket Cij. So where Cij equals ai1 b1j plus ai2 b2j plus ai3 b3j plus ... am b and j. So what does all that mean? Okay, so moving right along here, the definition of matrix multiplication indicates a row by column multiplication, where the entry in the ith row and the jth column of the product AB is obtained by multiplying the entries in the ith row of A by the corresponding entries in the jth row of column B, and then adding the results. The general pattern for matrix multiplication is as follows. So when we have A11, A12, A13, A1n, then A21, 22, 23, 2n. So that's the way we move across like this. And then B11, B12, Bij, B1p. So B1p would be our product here, B21, B31, and then same thing here. So we have our row, and then we have our column arrangements here. And then when we multiply two together like that, our C will be C11, C12, C1j, C1p, and then our Cij here will equal our Cij in this situation here will be A1, or rather AI1 B1j. So it'll be our AI1 will be our row I, and then column 1 times the B will be row 1 column j plus A times row I column 2, B will be row 2 column j plus AI column 3 times B row 3j plus ... AI and B and J will equal C. I will be row I and then column J. So we have to, when we move across on one multiplication, we're moving down on the other. So let's get an example to really point out in an easier way here. Finding the product of two matrices. Find the product AB using A equals -1, 3, 4, -2, 5, 0, and then B will equal -3, 2, and -4, 1. So when you multiply these two together, first note that the product AB is defined because the number of columns of A is 2 to the number of rows of B. So we have 2 columns here on A and then 2 rows here of B. Moreover, the product AB has a dimension 3 by 2, so it would be a 3 by 2 here. So we have 3 rows here, and then we have 2 columns over here. We have a 3 by 2 here. To find the entries of the product, multiply each row of A, each row here of A, by each column of B. So we're multiplying rows by columns, rows by columns. So AB would be -1, 3, 4, -2, then 5, 0, and then we're multiplying that by -3, 2, -4, 1. So we're multiplying rows here by columns. So when we know that, we're going to multiply -1, we're going to, again, rows by columns. So -1 times -3, and then 3 here times -4. So we're moving down on this one, and we're moving across on this one. And then our next one here would be -1 times 2 plus 3 times 1 here would be our situation here. So we've taken care of this row here has been taken care of. -1, -3, -1 times 2, and then 3 times -4, and then 3 times 1 here is what we've done. 3 times 1. And then we have 4 times -3, and then -2 times 4, -4 here, -2 times -4. Then we move over here to 4 times 2, and then -2 times 1. So we're always changing our product here each time we move across. We're moving across this way, and we're moving down like this on our other side here. And then we have 5 times -3 plus 0 times -4, and then 5 times 2 plus 0 times 1. So each time we move here, we're changing our products. We're moving this way and moving down this way by this product up here. And then what we do, we just add these products together, and we get, let's see, 3 plus -12 will give us -9. And then over here, -2 plus 3 will give us 1. And then -12 plus +8 will give us -4. And then 8 plus a -2 will give us 6. And then -15 plus 0 will give us -15. And then 10 plus a 0 will give us 10. Okay, here's I got to practice here for this concept here, and these exercises find AB if possible. So on number 35 here for A, we have a 3 by 2 here, 3 rows, 2 columns. And then for B here, we have 2 rows by 2 columns. And then we end up with this product over here. How did we get from here to here is the question. Well, to get from there to there, we're going to multiply this one by column, or rather by row by column here. So here's our row here, here's our column here, and we have 2 columns. So this will be, this multiplication here will be this position over here. So negative 1 times 2 would be negative 2, and then 6 times 0 will be 0. So 0 and negative 2 will be negative 2. So that's how we got that one. Now we need to get 51. How do we get 51? We're going to go negative 1 times 3 be negative 3, plus 6 times 9 would be 54. So 54 negative 3 would be 51. So that's how we got that number there. Okay, we're going to drop down now to the next row. Negative 4 and 5. We're going to multiply that by 20 now to get negative 8. So negative 4 times 2 would be negative 8. Then 5 times 0 will be 0, so we get negative 8 there. Now we're going to go for 33. Negative 4 times 3 be negative 12, plus 5 times 9 be 45. That will be 33 there. Now moving on to the final row here, we're going to go for this position here, 0 and 3. So we go 0 times 2 will be 0, and then 3 times 0 is 0. 0 plus 0 will equal 0. And then over here now for 3, 9 to get 27, we're going to go 0 times 3 is 0. Then 3 times 9 will be 27. So that's how we got that one. So now down here, we have a 3 by 3 here. Then we have a 3 by 3 here. So to get this product over here, we're going to this time we're going to go down by column by row now. Is how we're going to do this one. Either way, it still works the same. So we're going to go for this position here. So 1 times 3 is 3. That's how we got that one. And then 0 times 0 would be 0. And then 0 times 0 will be 0. So instead of adding everything together, we have a 3 by 3 in each one. So now we need 3 columns here for a 3 by 3. So we do not add our product together. We just comprise a row by like that now. Then over here for 0, 4, and 0, we have 0. 0 times 0 will be 0. 4 times negative 1 would be negative 4. And then 0 times 0 here would be 0 here for that one. And then for this column here, 0, 0, negative 2, that column by this row now, 0 times 0 will be 0. 0 times 0 will be 0. And then negative 2 times 5 would be negative 10. So this is how we got that product there, by multiplying columns by rows. And that is your lesson today, 7.5 part 2 pre-calculus math. If you need class worksheets, homework sheets, solution PowerPoints, email me here, animatedpowerpointmathvideo@aol.com. Thank you very much.